So you may ask, what's the purpose of a capacitor? Well, because they have this ability to store a large amount of electrical charge, then they're often applied in cases where you need a big discharge in a short amount of time. So every capacitor is rated by the amount of capacitance measured in farads. I don't know if you can see this one. It says it's 100,000. It actually looks like it says 100,000 megafarads. There's a capital MF, but that's certainly not the case. I just think the typeset doesn't include the Greek symbol mu for micro. This is actually 100,000 microfarads, which is kind of a funny use of metric prefixes. So it's 100,000 times 10 to the negative 6, which just would be the same thing as 0.1 farads. But microfarads are such a common unit that you often get funny sort of the use of scientific notation in this way. So yeah, so this is about a 0.1 farad capacitor. Think of that. This isn't even a 1 farad capacitor, and it's this large. So a farad is actually a large amount of capacitance. We often express it in either picofarads, microfarads, or possibly millifarads. So let's charge this one up and see what happens. I started to say that there's always two ratings, that not only do we know the amount of capacitance, but then there's a maximum voltage that I can apply. So this one has a 20 volt max rating on it. So I have my power supply set to about 15 volts. It fluctuates. Let me dial it up. Oh, it bounces around. Okay, well, hard to get it exactly 15.0. So if you see the number fluctuate, don't worry. Not all capacitors are polar. This one happens to be, so I have to pay attention to where the positive sign is and make sure that the positive terminal of my power supply is plugged in there. It takes a little bit of time, not much, for this to reach its full charge. So when I connect it, you might have seen the current jump up really quickly, but then eventually it settles back to about 0. At that point, our capacitor is saturated with charge, and you can't see it, you can't smell it, you can't hear it, but the charge is there. And so if we want to discharge it, then we should be able to recognize that I had stored charge. Let's see. Oh yeah, absolutely. Okay, boy. Would that be safe for me to touch? Let's try. I'm going to charge it up again. And it doesn't take long to get fully charged. Gosh, and when I touched it to metal last time, it crackled like crazy. Good idea or bad idea to touch this to my finger? Not a problem at all. Not a bad idea. Here's why. Because it wouldn't be a bad idea for me to just grab these wires in the first place. 15 volts of DC is not a whole lot, okay? So whatever voltage was used to charge it is going to be the same voltage that discharges it. We made an analogy earlier, a comparison between capacitors and balloons. If I used a very little bit of pressure to inflate this balloon, now if I suddenly poked a hole in it and let that air blow out and sort of let the air hit my skin, it's going to hit my skin initially with the same pressure that was used to inflate it. I can't deflate a balloon so the air comes out at greater pressure than was used to inflate it, right? So why does metal make all the sparking? Well, just because metal's such a good conductor. My flesh is not such a good conductor. So I've seen capacitors like this in the trunk of people's cars. And if you have a really powerful audio system in your car, there's not enough electricity that can be delivered by the car's battery to power the subwoofers when a big bass note hits. So if you're listening to the music turned up really loud and you have very large subwoofers in your car stereo, then you might need to draw the electricity out of a capacitor instead of the car's battery. So the battery is continuously giving a slow trickle of charge to the capacitor, and when the big bass note hits, suddenly, boom, you get the discharge to power it. We also see capacitors play a similar role to power the flash bulb in these disposable cameras. So if we take one of these cameras apart, we see a circuit board in here, and if we pull out that circuit board, it looks something like this. And we can easily find where the capacitor is. Now this capacitor, if you can read it, is rated at 330 volts maximum voltage and it's a 120 microfarad capacitor. 330 volts. I don't think a disposable camera has that much voltage available. It looks like there's just a 1.5 volt battery inside. But if we trace our way through this circuit board, we're going to find a couple of components. When the electricity comes from this battery, and here I've drawn a schematic diagram. So electricity flows in a loop. The electricity goes through a converter, and that changes the DC into AC. And then because it's AC, the electricity goes off to a transformer, and that steps the voltage up. It increases the voltage from 1.5, probably not all the way up to 330 volts, but up to a very large voltage. That process takes time, and that's why when you hit the charging button on these disposable cameras, you have to wait a while, and eventually a little LED lights up, and if you have good hearing, you actually hear this high-pitched sound because the transformer is acting at a high frequency. Anyway, then when you, if you close this switch, this is the switch that's charging up the capacitor. Then when you press the button to take a picture, that closes another switch that takes the electricity out of that capacitor and off to the camera flash. Okay, so there's the practical use of capacitors. Anytime you need a sudden large discharge, you can get it out of a capacitor. So let me show you the discharge you might get out of this one. Let's take a pen. See, I would never want to get this thing charged up to 330 volts and then have my finger touch that piece of metal and that piece of metal and allow something that was charged at 330 volts to discharge on my skin. Earlier, I showed you I don't mind applying 15 volts of potential difference across my body, but I'm not about to apply 330 volts. So if you ever take one of these disposable cameras apart, it's a really good idea to keep one hand in your back pocket. That way, the very worst that could happen is you might accidentally have one finger or something like that touch those, and if you get hundreds of volts across one finger, you're going to jump and scream and you won't enjoy it, but that would be far better than having your right finger touch that electrode and your left finger simultaneously touch that one, and then conduct electricity from 330 volts across your whole body. So keep one hand in the back pocket as a general rule. Let me push down on this button. That's the charging button. And you always have to wait a while for the capacitor to get fully charged because it takes time to transform 1.5 volts up to 330 volts. So after enough time, we should have a fully charged capacitor. And then it's nice to have a paper clip close by. And instead of my finger, if I touch the paper clip to both electrodes on the capacitor at once, then I can get a discharge. And sometimes you can even hear that discharge. Listen carefully. Could you hear that? Yeah.